Hello there, and welcome back. In this video, we're going to continue our discussion of the fundamentals of probability theory. In the last video, we introduced two important concepts, the sample space and the event space. So remember, the sample space of an experiment is the set of all possible outcomes of that experiment, and the event space, which is a subset of that sample space, is the set of all outcomes that we are interested in studying. So we define the probability of a particular event to be equal to the size or cardinality of that event with respect to the size or cardinality of that sample space. So one can think of the probability of a particular event as the likelihood that that event E occurs within that sample space. So of course one could go into the question, well, what does likelihood mean? So one could think of it this way. If the probability of an event is equal to 30%, one would expect that 30% of the time that outcome would arise. That doesn't necessarily mean that always 30% of the outcomes will be that particular event, but it means the expected outcome will be 30%. So let us look at an example of how to calculate a particular probability for a particular event that we may be interested in. So suppose you have 5 people, and let's assume all of the people are different, and they're standing in a line, and you ask all of them to shuffle around randomly for 10 seconds. After the 10 seconds is up, you're going to ask them to line up again. What is the probability that none of them are in their original position? If you want to try this problem on your own, I definitely invite you to pause the video and try it. And if not, let's just see what we have going on here. So let us just look at the sample space for this particular event, and then we'll take a look at the event space. So what does the sample space look like? So the sample space is all of the possible rearrangements of those 5 people. So I'm going to label those 5 people A, B, C, D, and E, just for notation purposes. So we have the original position, let's assume, is A, B, C, D, E. Let's assume A, B, and C do not move, but E and D do switch positions. So we have E and D. You could have A, B, E, D, and C. You could also have A, B, E, C, and D. And you could have a bunch of different rearrangements. For example, they could be backwards, E, D, C, B, and A, right? So those are all of the possible rearrangements of these people. So what do we want? We want the probability that none of them are in their original position. Okay, so we need to find the cardinality of the sample space first. So we actually at least have a description of S. So in terms of cardinality of this set, well, how many elements do we have? Well, we can think of the outcome line from this perspective. So we have position 1, position 2, position 3, position 4, position 5. And let's assume all of them are different. So if this is the case, let us assume we have 5 people. That means 5 people can be in the first position. Once that first position is filled, we have 4 remaining people that can be in position 2. From that, we have 3 remaining people that can be in position 3. 2 people remaining that can be in position 4, and whoever is left will be in this position. So this is the default place for the last person, right? So we say that there are 4 degrees of freedom for this particular experiment, one may say. So by the fundamental counting principle, one can say that the cardinality of S is going to be equal to 5 times 4 times 3 times 2 times 1, which is going to be 5 factorial, which can be found to be 120. So this is the sample space, the set of all possible rearrangements. Now let us look at all of the rearrangements that we are actually interested in particular where they're not in their original position. So A cannot be here, B cannot be here, C cannot be here, D cannot be here, and E cannot be here. So how many rearrangements? For example, the backwards permutation is not allowed. Even though E, D, B, and A are not in their original position, C hasn't moved, right? So that's bad. So what does our event space look like? So our event space has all of the values for whichever one has changed position. So we could have B, A, D, E, and C, right? So that's one possible permutation that satisfies that criteria. We could have D, A, B, let's go E, and then C. That's another element that is in this event space. So how can we count all of the rearrangements in this set? Well, that's actually just a derangement, right? So these are just derangements of the 5 objects, right? And we know a way to calculate the size of this event space via this derangement formula. So the cardinality of the event space is just going to be the derangement of 5 elements. And remember what that is. That's just going to be equal to 5 factorial divided by the Euler constant E plus 1/2. And one can find that's going to be approximately equal to the rounded down version of 44.65, which will round down to 44. So that's how many derangements of 5 objects there are. Now that we have the size of the event space and the size of our sample space, what does that mean? That means the probability that no one is in their original position is going to be equal to the size of the event space divided by the size of the sample space, which is going to be equal to 44 divided by 120, which is approximately equal to 0.366 repeated, or 36.7% approximately. So if you were to do this experiment infinitely many times, let's assume, you would expect that approximately 36.7% of the time, nobody will be in their original position. Now that we have the basics of probability theory discussed for a single event, now let us look at how we can discuss what is the probability of either one event or another event occurring, right? So possibly 2 or more events. So let's consider a sample space. Let's just represent it by a little box here. So let's assume this is the space of all possible events. Let's assume we have one event over here. Let's call this event A. Let's assume we have another event here, and let's call this event B. So what is the probability of either A or B occurring? So we represent this, at least in set notation, as the probability of A union B, right? So one can show via some logic and other approaches that the probability of A union B is equal to the probability of A occurring plus the probability of B occurring minus the probability of A and B occurring, right? So this is associated to the word and, this is associated to the word or, and from the set theory perspective, this is the union of the two events, and this is the intersection, or the overlap. So the intersection, or one could view it as the overlap. Intersection or overlap of the two regions. So this is called sometimes people call this the sum rule for probabilities. So this is the sum rule. Sum rule for probabilities. So let's just do a little Venn diagram practice, just in case you are not already aware. So let's assume this is A and this is B. So if we were to shade all of A and all of B, then this shaded region corresponds to A union B. And if we want to only shade the overlapping regions, so for example this little piece here, that would correspond to A intersection B. And if I just want to shade the individual elements, for example that's A and that's B, and let's assume this is A and that's B, they don't have to have any overlap, right? We usually call them disjoint events. Disjoint events. Some people will also use the word mutually exclusive events. Then if I want to graph the event A, right, so that's A, and if I shade this, that is going to be B, right? So it's just some basic Venn diagrams, VENN, DIAGRAMS. Venn diagrams can definitely help you in solving some basic probability problems, just in case you get stuck or visualizing some of these things. So again, the probability of A or B is going to be equal to the probability of A plus the probability of B minus the probability of A and B. So let's sort of think about what this formula is, what it means, and how we may be able to use it, right? So let's make them overlap just a little bit more. So if we want to find the entire union area, we actually have three individual pieces, right? So we have A, right? So that's A. Notice A includes three pieces. We have the exclusively A region, we have the exclusively B region, and we also have the overlapping region C. So A is actually equal to little a plus C. So little a is going to be this crescent moon region here. So it doesn't include the overlap, right? So A consists of the exclusively A and the overlap C. B consists of the overlap and the exclusively B region, right? So that's going to be this area there. So that's the exclusively B region. So that's what I'm calling B. Now let's assume I want to find A plus B. Well, A plus B should be little a plus B plus C, but when I add these two, notice that I get A plus B plus 2C, right? So we need to subtract one of these C's, one of these overlaps, in order to not count the middle elements twice, and that's pretty much where the sum rule comes from. So let us look at a particular example of how we can use this in practice. So let's go through the statement. I'll just pause this video, write it, and then unpause, so you don't have to see me write and talk for 10 minutes. Consider the following box of toys that I've graphed on the right-hand side. So the box of toys consists of blue toys, red toys, circles, and stars, as indicated as I have drawn. What is the probability that if you shake the box and then select one toy at random, that it is either blue or a star? So what is the relevance of this problem? Let us assume you're a person that is really happy if you get a blue toy, or you're really happy if it's a star. So if you get one or the other, you're going to be a happy kid, or a happy person in general. So, and one could think of this problem as equivalent, what is the probability of being happy? Alright, so the reason I mentioned this, what is the probability that you shake the box and then select one toy? Because if this is your box setup, you might be able to memorize the positions of these toys, so you don't want to have any biased sampling for this experiment. So we want everything to be random. So the probability of selecting one toy is not any different than the probability of selecting another, right? So a nice uniform distribution of probabilities for individual toys, all right? So let us look at the sample space. So the box of toys is the sample space. So what is the size of my sample space? So this is going to be the set of all of my toys. So I have 1, 2, 3, 4, 5 blue toys. So actually let's write that down. So the size of my blue toys is going to be equal to 5. What is the size of my red toys? That's going to be equal to 1, 2, 3, 4, 5, 6, 7, 8, and 9, right? And blue and red toys partition my sample space. So that's going to be 5 plus 9. That's going to be equal to 14. Now, that is not the only way to partition my sample space. You could partition it based on shape. So, for example, the size of my circles is going to be what? So I have, let's count them. So 1, 2, 3, 4, 5, and 6. So I have 6 circles. And how many stars do I have? So I have 1, 2, 3, 4, 5, 6, 7, and 8. Right? Again, circles and stars partition my sample space, so 6 plus 8 should be equal to 5 plus 9, which is indeed 14. Right? Now, partitioning sample spaces is going to be a very handy trick in determining probabilities later when the problem becomes a little bit more complicated. And you can ask several different things. For example, what is the size of the set described by blue stars? So blue and star, I guess you would say. So how many blue stars are in the set? There's going to be obviously 2 of them. Now let us look at our particular problem that we're interested in. What is the probability that it is either blue or it is a star? Keyword here, or, so not necessarily both. So let us write that down. So what is the probability that we have a blue or a star? So using the sum rule, that's going to be the probability of blue plus the probability of star minus the probability of blue and star. So how many blues do we have? So remember, the size of our blue set is 5, so the probability of blue is going to be 5 divided by the size of the sample space, 14. The probability of star is going to be the size of star divided by the size of the sample space it's coming from, which is 14. And the probability of blue and star is going to be 2 divided by the size of the sample space that that set belongs to, which is 14. So this is going to be equal to 5 plus 8 minus 2 all over 14, which is going to be 5 minus 2 is 3. 3 plus 8 is 11, so we have 11 over 14 as our fraction, which is approximately equal to 0.7857. So if your parent or guardian or whomever is giving you a box of toys and you're happy if you either select a blue or a star, if you were to conduct this experiment infinitely many times, you would be happy approximately 79% of the time, if this was the only thing that made you happy, of course. Now again, I did mention one term before that is going to be very important, and that is mutually exclusive events. So if the overlap A and B is the empty set, then we call that A and B are mutually exclusive events. So mutually exclusive events, right? So if two sets are mutually exclusive, then the sum rule, so a special case of the sum rule, special case, is that the probability of A union B, well in general, is probability of A plus the probability of B minus the probability of A intersection B. But if A and B cannot happen simultaneously, i.e. mutually exclusive, that means that A intersection B is the empty set. So we have the probability of A plus the probability of B minus the probability of nothing occurring, right? So what's the probability of that? Well, that's just going to be 0, so we're just going to be left with probability of A plus the probability of B, right? And that's going to be equal to that. And why is the probability of the empty set equal to 0? Because we're selecting one toy from the toy box. So if we're going to sample one element from the toy box, it has to be one of the elements from the set, not nothing. So that's a special case of the sum rule. In case you have events A and B being mutually exclusive. So for example, what is the probability of me selecting a circle or a star? If that is the particular problem, you can't be both a circle and a star. So the sum rule says you can just find the probability of a circle, probability of a star, add them together, and then you are done. So that's just a basic example of the sum rule and a special case for mutually exclusive events. So now let us consider another type of event that is extremely common in practice. So suppose that one event actually affects the outcome of another event. For example, let us assume you have a random person, and let's assume you're an agreeable person and you like that person, or not. Then most likely if that person is random, there's a probability that you will like them on the surface. But if they start yelling at you or being rude or mean, the probability that you like them most likely will decrease from what it used to be. That would be dependent events. So let's look at another example that we're going to sort of work with. So let us assume we have happiness, right? So if I were to choose a random time throughout the day, the probability that you are happy is going to be approximately 85%, let's assume. But some people are affected by the weather. So what is the probability that you are happy assuming that it's raining outside, right? So what is the probability that you're happy assuming that it's raining outside? Usually this is going to be lower or maybe even higher than it used to be. Let's assume it has a negative impact on your probability. So in this case, rain has a negative impact on your happiness, right? So that's not good. So regardless if it goes up or goes down, then we say that these are dependent events. So what is the dependent events? The dependent events are happiness and rain, right? So let's assume that rain does not change the happiness of you on any given day, right? So another example. Let's assume the probability that you are happy is again 85%. And let's assume the probability that you are happy and there is no money in your bank account. So probability that you were happy, assuming you have no money in your bank account. Right? Let's assume that this is also going to be equal to 0.85. Right? So notice here that the probability has not changed. Right? So how do we interpret that? That means money has no effect on your happiness. From the probabilistic perspective, we refer to these events not as dependent, but independent events. So independent events. Now, in terms of notation here, notice that these things after the bar is the thing that has already occurred. Right? So these two things here already occurred. Some people will refer to this as the condition of the probability. So let us try and summarize this in a more general, more formal manner now. So independent versus dependent events. So if A and B are independent events, then the probability of A, assuming B has already occurred, is going to be equal to what? Well, if A and B are independent events, A doesn't really care if B happened or not. That means the probability of A given B is just going to be equal to the probability of A. Similarly, if A and B are independent events, what is the probability of B occurs, assuming A has already occurred? Well, if B and A are independent events, B doesn't really care about whether A occurred or not. So the probability of B given A is just also going to be the probability of B. So these are our conditional or independent conditional rules. So now let us look at conditional probabilities from the Venn diagram perspective. So let's draw a little Venn diagram here. So this is going to be my sample space. And let's draw this event. This is going to be my event space. So this is going to be my cardinality of E. And notice if I ask you what is the probability of E, the probability of E is going to be equal to the size of E divided by the size of the sample space. So the sample space is the set of all possible outcomes that could occur, right? So you can sort of think of an experiment as once you conduct that experiment, the entire sample space has been activated. You must be selecting something from the sample space. You might not exactly know what that is, but it definitely has already occurred. So technically speaking, the probability of an event can always be written as the probability of event assuming that the sample space has already occurred. So this is generally always going to be true. Now, what if another event has already occurred, right? So let's assume we have our sample space here. And again, here's my event space E, but let's assume there's another event here that's sort of hanging out. So let's assume that, let's just do a baby sample space. Right? Let's assume this is sample space T. Okay? So what is the probability of the event E assuming T has already occurred? So if T has already occurred, that means this is the new sample space for my event, right? Because if T has already occurred, that means only these things in this green box can occur next. So if that is the case, that is going to be equal to the size of E with respect to that set, right? Which is going to just be the overlap, right? So that's going to be the probability of E intersection T all divided by the probability of T. Of course, E need not be a proper subset of T in order to make this true. For example, I can have E here. I can have another set T here. So what would this again be? So if T has already occurred, that means this is my new sample space. And the only possible way that E can occur is going to be this little region here. Again, this region is the overlap of E and T, but now we're going to be dividing E by the size of T, so it's just going to be pink divided by green instead of pink divided by the entire sample space, which would be hanging out here. Right? So what a conditional probability does is it creates a new sample space. Because remember, the sample space is usually on the bottom of our probability calculations, so T is acting like our new sample space, which is pretty interesting. So with this new rule, so some people just take this as the definition of a conditional probability. So the probability of A given B is going to be the probability of A and B occurring all over the probability of B. We can actually solve this equation for the probability of A and B. And that gives us what we call the product rule for probabilities. So the product rule for probabilities. And these are this. The probability of A and B occurring simultaneously is going to be equal to the probability of A. Actually, I'll just do B first. So it's going to be the probability of B times the probability of A, assuming B has already occurred. Or you can do this reversely because A could happen first. So that's going to be the probability of A times the probability of B given A has already occurred. Now, is there a special case for the product rule for probabilities? Yes, indeed. So a special case for independent events, right? Because if these events are independent, then A doesn't really care about B and B doesn't really care about A. So the probability of B given A is just going to be B. The probability of A given B is just going to be A. And that means the probability of A and B is just going to be equal to the probability of A times the probability of B. So this is a special case for the product rule for independent events. And we also have one more special case, and you might be able to guess what it is, and that is mutually exclusive events, right? So if they are mutually exclusive events, that means they cannot happen simultaneously, which means the probability of A and B is equal to 0. So those are some of the basics of the product rule for probabilities and sort of how they connect to conditional probabilities. Now let us go back to our toy box example and let's see if we can use the product rule to solve a couple of the problems that on the surface seem easy to solve. And you probably could solve these without the product rule, but it's just here to sort of give you an idea of how to use it just in case it's not easy to, for example, list the sample space out, all of the elements in it, and that also goes for the event space as well. So what is the probability? So example, let us assume you pick one toy at random after you shuffle all the toys in the box. What is the probability that it is a red star, right? So what you could do is you can count all the red stars, divide by how many total toys you have, and that'll be your probability, right? But let's assume you can't count all of them or the sample space isn't obvious, right? So what we can do is we can use the product rule. So what is the probability that it is a red and a star, right? So from the product rule, that's just going to be equal to the probability of red times the probability of star, assuming that red has already occurred, right? So what is the probability of red? So the probability of red is going to be equal to 1, 2, 3, 4, 5, 6, 7, 8, 9 divided by the total elements 10, 11, 12, 13, 14, right? So that's the probability of red, and notice that that is corresponding to my original toy box. So what does that mean? So now, since red has already occurred, our next event is going to take place there, right? So now our new sample space, because they have to occur simultaneously, right? So that means our new sample space is going to be this set, right? So that's our new toy box, I guess you could say. So what is the probability that we choose a star, assuming that our first choice was red? So if that is the case, well, how many stars do I have in my new sample space? So I have 1, 2, 3, 4, 5, and 6. So that's going to be 6. And what is the size of my new sample space? So that's going to be 7, 8, and 9. And the product of these two fractions is going to be my probability. Now, of course, do notice these 9's do cancel, and you're just going to be left with 6 over 14, which is, of course, the same thing. So 3 over 7, which is approximately equal to something, I guess you could find. But that is the same exact probability that you would get if you just look at the original sample space and count all of the number of red stars and divide by my entire toy box sample space. So you do get the same exact thing, but this is really useful when you do not have the ability to list all of the possible sample spaces, events, or the event spaces, or maybe you just want to ignore the blue space altogether. So in this case, that would be an example of when you could do that. So let's just summarize all of the rules that we have discussed so far in this overview of probability theory. So the sum rule has the following relationships. So the probability of A union B is going to be equal to the probability of A plus the probability of B minus the probability of A intersection B, the overlap of the two. Now, if these events are independent, then we can write this as the probability of A plus the probability of B minus, so if A and B are independent events, then that's just A times the probability of B. And if they're mutually exclusive, then that means the probability of A and B is just equal to 0. So that's going to be equal to, well, technically I can do an independent step here because they don't need to be independent. But how would you find the probability of A and B? So in general, you can do probability of A assuming B has already occurred. That would be okay too, right? And then we can do our special cases here. So probability of A plus the probability of B minus the probability of A times B, right? And that's going to be the probability of B, of course. And then mutually exclusive would be what? The probability of A plus the probability of B. And then let's just summarize our product relations. So that's going to be equal to the probability of A intersection B. Generally speaking, that's going to be a probability of A times the probability of B given A. Or you could do the probability of B times the probability of A, assuming B has already occurred. If they're independent, that's going to be the probability of A times the probability of B. And if they're mutually exclusive, that's just going to be 0. Right? So those are your, I guess, 7 rules that you could use for probability theory. So with that being said, let's look at just one more special occurrence that you'll most likely run into at least once. So the last concept that I want to introduce today is the complement of a particular event. So let's assume A is a subset of S. The complement of A, denoted by A with a little c on top, is the set of all objects in the sample space that are not in that particular event A. So let's just look at if we look at a sample space S, and let's assume that this set is our sample set A, then the complement of that is going to be all of these events here, right? So this is going to be a complement. Now keep in mind that A and a complement do not share any overlap. That means A and its complement partition a sample space every single time, which is actually a pretty interesting thing, as long as A is not an empty set, of course. But that's a special case, right? So if A and a complement partition a sample space, what does that give us? So that means the probability of A plus the probability of its complement must be equal to the probability of the sample space, right? Because they are disjoint events and they must sum up to all of the values in the set. And we know that the probability of something occurring out of everything is always going to be equal to 1. So from this, we can get a formula for the complement. Probability of A complement is just going to be 1 minus the probability of the original event. And you can, of course, rearrange that if you want to. So let us look at a particular example of where we may want to use this. So let us suppose you roll 2 6-sided dice let's assume they're listed from 1 to 6. What is the probability that the sum of the outcomes is greater than 3, right? So our event space, E, is getting a sum greater than 3. So remember, we listed out all the values in the sample space, right? So the sample space consists of all outcomes like 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, and so on, right? So we found that the size of the sample space was 6 squared, which was 36. Now, what does the event space look like? So we want a sum greater than or equal to 3. So if we actually just look at just these first few elements, 3, 1, 3, 2, 3, 3, do notice that all of the values that gives us a sum of 3 are 2, 1, 1, 2, and also a sum of 2, which is also less than 3, is 1, 1. So all of the values below this baby triangle will be, so this value gives you a sum that is bigger than 3. So do we really want to count all of those elements? No, because we have very few elements in the complement of the set, right? Because this is our complement, and this is our original set that we're interested in. So if that's the case, that means E complement just consists of the elements 1, 1, 1, 2, and 2, 1. And we can easily find the size of that complement is going to be equal to 3. So if the size of the complementary space is 3, that means the probability of the complementary space is going to be equal to 3 out of 36. If that's the case, how would you find the probability of the original event? Well, that's just 1 minus the probability of its complement. So that's going to be 1 minus 3 over 36, which is going to be 33 over 36. And you can find that decimal if you so wish. Now, one more thing about complements. Do we have to create new rules for the unions and intersections involving complements? No, not at all. So for example, how would you find the probability of A union B complement or something like that? So if we just use the rule, that's just going to be the probability of A plus the probability of B complement minus the probability of A intersection B complement. Typically this is known, or the complement of A. Typically this is known, or the complement of B complement, which is the original set B. But this is usually not known at all. So actually let's take a look at the Venn diagram of how we can think about that. A intersection B complement, right? So remember, if this is A and this is B, what does B complement look like? So B complement is the exterior of set B, right? So whereas A is going to be this whole circle here, but notice that the overlap between them is practically A, but without that overlapping middle part, right? So, oh no, I deleted my B. There it is, right? So if that is the case, we can sort of think about A intersection B complement as, so the size of that is just going to be equal to the size of A minus the size of A intersection B. Okay? So if that is the case, that means the probability of A plus the probability of B complement. So how are we going to deal with that? That's just going to be equal to the probability of A minus the probability of A intersection B, right? And then we can distribute this negative sign. Our probability of A's will cancel, and we're just going to be left with the probability of B plus the probability of A intersection B, right? And that's going to be the probability of A union B complement, and you can apply some applications to that problem. So those are some very important and very commonly used properties associated to basic probability theory. In the next video, we'll just build on that, look at a couple special cases, and then after that, we'll look into some special extensions that can make probability problems so much easier. So I'll see you then, and take care.